Good morning, everyone. My name is Gary Corley from Kirby Smith Machinery. I'd ask if you would stand by for just a few moments. We're waiting for a few more folks to sign on, and then we will commence in about 3 minutes. Thank you. Madam Producer, I'm ready to proceed.
Please go ahead, sir.
Good morning. My name is Gary Corley from Kirby Smith Machinery. I want to welcome you to the first of a series of webinars on asphalt paving training that we'll be offering in conjunction with our friends at Hum Morgan. This webinar series is representative of Kirby Smith's dedication to training and promoting quality in the asphalt paving industry. Today's topic is basic compaction, or Compaction 101, and will be presented by Tim Kowalski, who is the Application and Support Manager for Hum Rollers. Tim has a bachelor's degree of science in construction management from the University of Wisconsin-Madison, and is a veteran of 23 years experience in the construction industry, focused on quality control issues in the asphalt industry. I think you will enjoy Tim's presentation this morning. During today's presentation, we invite you to post any questions that you may have in the chat area located on the right-hand side of the screen, and I, in turn, will pose your questions to Tim. Our presentation should run about 45 minutes in length, ending at about 8:15. Tim, if you're ready to go, I'll turn this over to you.
I'm ready. Well, first of all, I want to thank Kirby Smith for inviting me in to do this webinar, and thank everybody for joining me in participation in the webinar as well too. So what I wanted to start out with, let's see if we can. The first one we want to look at is there is another session that we are going to be doing on May 7th, which actually is more of an advanced compaction class for the Kirby Smith webinar that they're looking at. So please make note of that. That will get into more in depth about compaction, the science, the techniques, different things that we look at when we're looking at compacting in the field. So we'll see this slide again at the end of the presentation so that you can grab that information as well too. So, but if you go to the Kirby Smith website, you should be able to find that information as well too. So just to get started, I wanted to talk a little bit about HOM and where we came from, kind of give you the history background of what we've been doing through the years. We're going to start out with the compaction basics. What is compaction and why do we compact? And then we'll talk about the 4 different elements of compaction. We'll talk about roller trains and how they can vary depending on with different specifications based on the states, the locations, requirements, mix designs, and so forth. We'll talk about the different roller types that are out there and how things have changed through the years based on the types of rollers that we are using because of the types of mixes that we are working with. And then we'll kind of summarize everything from there on what we just discussed. So if we look at HOM, we've been, actually last year we were 101 years old. So we've been in the roller business for quite a long time. This year it's actually 102 years old. We are not the oldest part of the business within the working group, but we are definitely got a lot of experience behind our belt. This kind of gives you a timeline of different things that have happened through HOM's history. And you see in 1956 we had the static 3-wheel roller. Well, that design hasn't changed much through the years, and we probably still see a lot of those around. 1963 we developed the rubber tire roller. Again, another design that hasn't changed much through the years, but we have made some changes to that recently. One of the things that will come up not only in this presentation, but the next presentation as well too, is a feature that is called oscillation. That we developed in 1983, and there's a history behind how and why we came up with the oscillation. We got soil rollers. We have small compact HD rollers as well, and also we have new generation coming out of our soil rollers as well too. HOM's factory is over in Tirschenreuth, Germany. We have about 750 employees over there. Like I said, it's a younger company, or an older company, but a younger company within the working group. It was acquired by Workin back in 1999, and what you see there on the screen is what the black roast is what we purchased back in 1999. Since then, we have developed and expanded that facility quite a bit based on the demands that are needed for the rollers, not only in the world, but in the U.S. especially too. So we've expanded. We've built on an awful lot. We definitely have expanded. We also had an outside source that was building all of our drums for us, and they could not keep up with the demand that we were looking at for our rollers. So we ended up building our own drum plant and supplying our own drums for all our rollers, as well as now for our mills as well too. So when we look on the soil side, we got 37 different models, anywhere from 5 to 25-ton models. Smooth drum and pad foot drums. This year with the now, everybody I'm sure has heard of the Tier 4 motors that are coming out, we have changed the design a little bit of our soil rollers, and we've gone to the H series. A lot of the same functional features that you've seen in our 3000 series, but with a lot of Tier 4 initiative for design on the engines. Moving to the tandem rollers, we have our HD compact line, anywhere from 1.5 to 5 tons, with mechanical offsets, tapered hoods, ease of visibility. We have our HD series, which is actually our older series of our tandem rollers, anywhere from 7 to 12 tons, which were initially brought over to the U.S. And now we have what we call our tandem rollers, our HD Plus models. We've actually taken everything that we've known or had on the HD models, listened to the operators of what they would like to see on the HD Plus models, and put it on the HD Plus models. A lot more functionality, easier operator use, and we have those anywhere from 10 to 15 ton rollers as well too. We go into the rubber tire rollers. We have now with our new GRW 280, we have a modular system as far as adding weight. Instead of for ballast, we can change the weight of a roller by adding or subtracting weights using a forklift. Where before the old styles, you put enough ballast in, that was kind of much what it stayed. But we have anywhere from 5 to 30 ton ballast rollers now. Another thing about Tom's history, when we first started out, those are the number of rollers that we sold per year. I think in 2009 was a bad year for a lot of folks. But if you look at last year, that 1,540 is an estimate of what we did. We actually did 1,558. Thinking of that number, based on where we started back in 2000, we were at about 2% of the market. With that number, this last year, we are up to about 24% of the market. So we are gaining a lot of recognition in the United States as far as being one of the leaders. Okay, enough about Ham. Let's get into a little bit more about what we came here for, and that's Compaction 101. So why do we compact? Well, we have a lot of different things that we try to compact. We look at hydropower plants. We definitely want to make sure that the material is compacted there to hold the water back. Otherwise, that makes a mess. Building pads, some of the size of the skyscrapers that we are producing and building, we definitely want to make sure we got good, sturdy material that we're building on top of. Airport runways, do a lot of travel, and I'm sure glad that they hold up under whenever we land and take off, because we definitely want to make sure that those stay together. But the main thing we probably deal with most is our roads and streets. We definitely want to make sure that we are compacting and getting the compaction we need for longer lasting and safer roads for everyone to utilize. So when we look at some of the important characteristics of soil and asphalt, we definitely want to make sure that they have a high load-bearing capacity. We definitely want to make sure that we get the compaction so we don't have loose soil that we're trying to stabilize. Good stability, that it won't move around if we do have any kind of disruption or disturbance. We want low water permeability, because if we do get water into either the soil or an asphalt, we know it's just going to deteriorate and fall apart, and we're going to lose our load-bearing capacity and stability of that material. Extremely level. The more level we can make the bottom surfaces, the more level we're going to be able to make the top surface. It used to be that just put it in and we'll worry about it when we get to the surface, but that's not the way. That's not truly how it works. The more level we can make it on the bottom, the easier it is to make it level on the surface. Well, we also, by doing so, we also make it the material to be a longer service life. And we have a high skid resistance. And I throw the high skid resistance in it because it goes back to the extremely level and being smoother. The more contact that we can have with our tires on the surface of the road, the better the skid resistance it is we have. You never notice when you go around a curve or on a road that's bumpy, your vehicle starts sliding sideways or hopping sideways. That less contact means that we're not going to have good skid resistance. So when we talk a little bit about soil materials, there are some important parameters that we need to look at there too. We have basically two different types. We have a cohesive and a non-cohesive soil. A cohesive soil is a soil that if you add a little moisture, it's got enough clay and silt content to it that when you squeeze it together, it'll hold its form. A non-cohesive soil is more of a single-sized aggregate or a material that doesn't have any bonding properties when you add any moisture to it. You try to compact it or compress it, it won't hold its shape. That's just a general consensus about the difference between cohesive and non-cohesive. And when we do compact, we do create friction, and the only way we can reduce that friction is by adding water on the soil side. So water content is very important on how we're going to get our compaction with the material. We also have to deal with the particle size distribution or our gradation curve. We want to make sure it's very evenly distributed so that we can get all those particles put in its place to build a good structure in base material. When we talk about particle shape, if we have all particles that are round, it's going to be like trying to roll marbles. They're not going to have any what we call aggregate interlocking together. They're not going to have very good load-bearing capacity and not a very stable material. So we do want to have some angular material in there to give some good structure and rigidity to that material in our soil. It also depends on the coarse thickness. How thick are we laying this? So are we putting it 4 inches in, or are we putting it 1.5 feet? A lot of that will decide, too, on the size roller that we're going to utilize based on the depth of the material that we're going to be putting in place. So when we talk about static linear loading, most all manufacturers will tell you what kind of loads you actually have on the front and rear axles of a machine. There are some locations in some states that will require certain linear loading per roller based on the material that you're going to be compacting. So the way we do this is basically taking the axle load of the front drum and dividing it by the roller drum width will actually give us the static linear load either in pounds per inch or kilograms per centimeter. This also can be done on the force. We'll also have a force generated on that front drum, so you can get not only the static linear load, but you can get the force linear load per inch as well, too, in the same manner. Some locations, like I said, do offer or do require specifications and rollers to be of certain size and have certain static linear loads and certain force loads. So it's a quick, easy way to calculate, and most all manufacturers will have that information in the spec sheets of the machines. When we talk about smooth drums, we have basically two different types on a saw roller. Like I said, we have the smooth drum rollers and we have the pad foot rollers. The smooth drum rollers are mainly used when we need an even, uniform surface to be produced. We also use them on a much larger stone material or a less cohesive or a road-based type material where it's not really induced with either clay or silt particles. Now, when we look at a pad foot drums are used more in earthwork for cold recycling. They kind of rough up the soil. If it's a higher clay content material, we can actually kind of dry the material out based on the shape of that pad foot. Now, the reason why the pad foots are shaped the way they are because it does increase the surface area of what it is we're trying to do. By doing it, there's two things. It increases the surface area to dry out the material, but also the shape, the way it's tapered, actually squeezes the material as you compact into it with the pad foot against the other pads. So now we create a greater force of squeezing that material together and trying to get the compaction, taking out some of the moisture. But the surface area is much greater, so we can actually get reduce some of the moisture that's in there. Now, there is a big discrepancy. A lot of people call a pad foot a sheep's foot. A lot of people call a sheep's foot a pad foot. There are two major differences in those two roller machines. A sheep's foot is actually what it looks like. It actually is a small, very low displacement as far as the soil goes, but a very high PSI based on the looks and the shape of the drum itself. It actually is a small surface area. It is a sheep's foot look like, and we actually use it more on higher clay soils. Looks totally different than what we have for a pad foot roller. So when people call sheep's foot, those are kind of gone by the wayside, and if they are a sheep's foot, it is something that we're probably going to be towing behind versus something that we're going to be driving. We also have what we call the smooth drums, both vibratory for the smooth drum and also vibratory for the pad foot as well too. So we do have vibration for both rollers. And then you also might see something out there what's be dragged behind again too is called the grid roller. When we talk about asphalt materials and some of the important parameters that we look at, we talk about mixed type. There are several mixed types that are out there, and every state has their own type of mixed nomenclature, but basically they're pretty much put together the same way. But with the different mix types, we need to be careful on how we're going to probably roll each of those mixes. With that mix type comes the particle size distribution curve or the gradation based on the type of mix that we're actually going to be using. Is it a coarse mix? Is it an SMA? Is it a Marshall mix design? A super paved mix design? What it is we're trying to look for. The binder type and proportion. The type of AC that we use has changed through the years, just basically on nomenclature. We have gone to what's called PG graded binders. We have some that are just straight asphalts. We have some that have some polymer modification to it. We have some that have rubberized modifications to it. So understanding those characteristics of the type of oil will also determine what kind of compaction effort we're going to need to have and temperature ranges we're going to need to be within. We also throw another thing in there called warm mix. That's another one of those things that have been coming out and about that really change on how we're going to look at compacting the material. But some of the things that we don't have control over, we call is environmental conditions when we pave. And when we call temperature, there's basically three temperatures we need to look at. We have the base temperature, we have the mixed temperature, and we have the air temperature. One of those three we can actually try to control fairly good, and that is the mixed temperature itself. We can control it at the plant, we can control it on the hall. Hopefully we can control it when we put it through the paver and try to get it compacted. The base temperature and the air temperature, that's dealing with Mother Nature. And hopefully she will abide for what we're trying to do. Also, same thing like in the soils is coarse thickness. Are we laying a 1-inch overlay or are we laying 4 inches deep? That will determine how we are going to set up the roller to compact that material. Are we going to use high amplitude, low amplitude, high frequency, low frequency, static material, oscillation, whatever we're going to use? We need to identify the mix type, the binder that's in it, and the coarse thickness that we're going to look at. So why compaction? We don't want things to fall apart. And again, it all starts from the bottom up. If we do not have a good base to start with, we are not going to have the surface. I've heard so many times through the years that, we'll just put more asphalt on it, it'll bridge it. Well, eventually it's going to start sinking because we're not going to have the proper compaction on the base. We're not going to get good compaction up on the surface. So we're going to struggle. It all starts from the bottom up. So again, why do we want to compact? We want to improve the material stability. We want to minimize permanent deformation or rutting, because if we don't get the proper compaction and we start putting traffic on this material and we create ruts, it creates a safety hazard in a lot of different areas. If it rains, that just becomes a big water trough, and when it becomes a water trough, we have what's called hydroplaning. That's very dangerous for the public on the roadway. Also, if we get up in the northern states in the wintertime, that water or snow, when it gets in there and freezes, now you just got an ice skating rink. So we definitely want to make sure we're getting the proper compaction to reduce the amount of running. That also has to do with the type of mix designs we're using too. We want to have the proper mix design for the proper location for the weight and traffic that we're going to be running. We also want to improve the fatigue resistance cracking. If we have cracking in the material, where do you think the water is going to go? It's going to follow the path of least resistance. And if there's a crack in the road, the water is going to find it. When the water sits in those cracks and we have vehicles going over top of it, it's going to create a hydraulic pressure from the tires pushing down on the water in that crack. And there's two things that are going to happen. Either that water is going to try to come out of the crack, and when it does, it's going to grab anything that's attached to it or around it in the surrounding area and come out with it. Normally, it's the fines in the mix. If it's not going to come out through the crack, it's going to force it further into the material, therefore putting a pressure on that bond between the asphalt and the rocks, and probably strip the oil off the rocks, therefore stripping, creating raveling, creating potholes. So moisture, not only in the soil side, but in the asphalt side, is not a good thing. So by reducing the amount of cracks, we will reduce the amount of moisture that we get into the material or the mat and have longer lasting pavement. So we definitely want to reduce that moisture penetration by reducing the cracks in the surface. So whose job is compaction? Well, it's everyone's job. And I hope no one here is from the Arizona DOT, but I always got to watch where I put that one in. So what is compaction? Really, it's just a manipulation of material to reduce to a certain void content, whether it be in soils or whether it be in asphalt. We are just basically manipulating this material to achieve a certain density or a certain void content that we feel is going to be give us the proper stability and load-bearing capacity for what we're going to use it for. Now, on the soil side, like I mentioned before, when we start compacting it, we increase friction or create friction. Well, how do we reduce friction? We add some kind of a lubricant. So on the soil side, it's really what we call a Proctor test. And we have what we want is we're looking for the optimum water content. That optimum water content is going to give us enough lubrication to where we can manipulate all those aggregate particles into shape or into a form that gives us the best compaction. If you notice on the left-hand side, if we don't have enough moisture, or enough lubricant, the part is going to have more space in between, and it's not going to give us a good load-bearing or stable material to work on. We go on the other side of the curve where we add too much water. Now we know we cannot compact a liquid. So once that moisture dries out, now we have the same condition we have on the far left side with not enough water. So we have an unstable material as well. So we want to find out what that optimum water content is by doing either a standard or a modified Proctor test in the lab to find out what moisture content is going to make us achieve the best kind of compaction in the field. On the asphalt side, we are not going to get to 100%. We want to have some kind of air void content in there. Typically, most mix designs are designed around 4% voids unless you get into like an SMA or an open graded friction course mix. But most of the time, we're around 4% is where we design the mixes. And that's usually after about a 7-year lifespan, we anticipate that mix to be down to about 4% voids. So we can achieve anywhere from 90, well, most of the time, anywhere from 92 to 96 is a range that they usually give us to. So that means we're anywhere from 8 to 4% voids in our mixes. We would like to see around maybe 5 to 6% voids would be ideal to give us a good long life pavement. Well, how do we measure the compaction? Well, in the lab, there's a couple different ways. We used to have the old Marshall mix design method that had a Marshall hammer, as you see on the left-hand side. We have now gone through and made a change to try to simulate a little bit more of how we compact things in the field by going to what we call a gyratory compactor, which is on the right-hand side. So we compact a certain size puck or pill, whatever you want to call it, and we'll try to measure those voids by weighing it in the air and then weighing it underwater and comparing how much moisture was soaked into that material to give us an air void content. Well, in the field, it's a little bit different. We can't necessarily pound out a puck, but there's a couple different ways we can do it. We can use either a nuclear density gauge or a thin lift gauge on the left-hand side or a non-nuclear gauge, what you see on the right-hand side. That's a non-destructive way. And usually those two gauges need to have some kind of a correlation to what we call a core. So if you really want to identify what an actual density is of a mat at any one particular point, we can actually take a core and run the similar tests as we did in the lab on it to find out what kind of moisture content is going to be absorbed into that core to figure out what our moisture or what our density is of that material to make sure we've got the proper compaction.
Tim,
what are the 4 elements? Yeah.
Could I ask a quick question here?
Sure.
Can you touch on the significance and the importance of the base preparation with regard to stabilization as it impacts hot mix compaction?
You mean for like full depth reclamation?
Well, no, more so the preparation of the base material for how that directly impacts what we're trying to accomplish with the asphalt pavement surface.
Well, a couple things. The same thing, just like when we deal with hot mix. Same thing on the base materials when we're creating a base for the asphalt to be on top of. Number one, we want to have a very consistent gradation. We don't want to have segregation. If we have segregation, we're going to have areas that we're not going to get good density and good stability. So the same thing applies on the base side as it does on the asphalt side, where we want to have consistent material. We want to have good material that we're going to be able to, that's going to be stable and going to give us a good load-bearing capacity, have some fractionation to it so that we have aggregate interlocking, and just make sure it's consistent, because if we have any kind of segregation, we're going to run across the same issues we have on hot mix. Is that when we have segregation, we're going to reduce the life expectancy of the mat, because more than likely we're going to reduce the density, and we're probably going to have some kind of raveling or pothole in that area. So the same things apply to the base as they do the asphalt side, as consistent gradation, consistency, fractionation of the material, and making sure we don't have any segregation. Does that answer the question?
Yes, sir. Thank you, Tim.
Okay. So moving on, what are the 4 elements to achieve compaction? Well, we have really what four different types. We call static weight, we have impacts, we have dynamics, which is more like a vibration or an oscillation. And then we have kneading, which we actually look at with our rubber tire rollers, or we actually can throw in with oscillation in with the steel drum. Doing a very similar thing with the oscillation. So here again is the three-wheel roller that hasn't changed for years and years. But years and years ago, the types of mixes that we had didn't have the fractionation in the gradation of the material, so it was very easy to compact, and we didn't have to add any vibration. There are locations that still use three-wheel rollers out there because of their high PSI weight to the depth or the width of the drums that we use. Most of the time it's used either on shoulder work, or some people actually use it for a finished roller on surface compaction. The other one is the rubber tire rollers. We look at the kneading effect. Where it really shines is you can use it both on base material or on asphalt materials when you have any kind of uneven surface, or especially on the asphalt side, if you have a lot of catch basins or manholes or water mains. If you have a steel drum, a lot of times that'll bridge over the hard spot, and you won't be able to get compaction around those things. The rubber tire roller with the uneven surfaces, it actually kind of kneads that material around, and you'll be able to achieve the compaction on very uneven surfaces. Now, looking at it on the asphalt side, there's a couple other different advantages too. Actually, the rubber tire roller really compacts from the bottom up by kneading that material in between the tires and managing it to where it almost walks itself out to the top, kind of like what a pad foot roller would do on the soil side. It also helps pull the fines to the surface to help seal the surface, which reduces that cracking that I talked about before, so we're not inducing any kind of moisture in the material. The key thing about a rubber tire roller, though, is tire pressure and weight. We want to make sure we have a good, even pressure for the size and weight of the roller. Now, that will be determined based on the tire manufacturer. And a lot of times, each tire manufacturer will have some kind of a chart to tell you what kind of PSI each tire needs to be at based on the axle load of the roller. We want to make sure that it's got a good pattern to displace that weight from that tire to the material to get that good kneading effect in between. If we have too much air pressure or too much air pressure for the weight of the roller, we have what we call a knifing effect. And instead of trying to knead that material in between the tires, it's actually cutting it and actually taking away some of the density that we're trying to achieve. So tire pressure at too high or too light of a roller for the type of air pressure that we're using is not going to help us as well either. Now, on the other side of that, too, we also have what we call a cupping effect, or if we have too heavy of a roller or too light of a roller for the pressure that we have in there, it's going to look deflated, and it's actually going to cup that material trying to pull it underneath the tire. Well, that's just the opposite of the theory behind a rubber tire roller, to push the material and knead it between the tires. This is also the fact that if we have a flat tire, you'll be able to tell exactly what tire on the roller is flat, because it'll make one ugly looking streak down the road, and you'll be able to tell pretty quick. So tire pressure is very important based on the weight of the roller that we're using, and most of the time tire manufacturers will have some kind of a chart to tell you what the PSI or pressure needs to be in the tires to get the proper footprint that we're looking for in a rubber tire. So looking at that, it provides a very effective way to compact within the tender zone, especially on some of the new super paved mixes. It helps knead that material back together and bond it up. We also look at impacts, but impacts really not necessarily so much for the asphalt side, but we can use it on the soil side. We can use drop hammers. We also have some other extremes that we look at that go to some varied depths. But these are some different methods that don't really require rollers, but it is still a way of compacting. So when we look at some different soils, we have a look at high amplitude and low frequency is kind of designed for some soil. In some areas, we do have some different ways of compacting, but this is something we don't need to worry about too much in the U.S., but it does come up into effect. Now this one here is where we have developed from the static rollers to find out what the different mixes that we're doing with the fractionation that we have to deal with. There's another energy that we need to put into the compaction effort to help organize or help compact this material. And hopefully you will be able to hear this when I play this.
I saw a demonstration where they took a clear cylinder and filled it with different sizes of beans to represent the hot mix. They took a small drill and attached a couple of washers a little off-center to act like an eccentric, Then they turned it on and held it next to the plastic. Oh, you could see those particles move. It compacted the mix at the same time. They said it works similar to that in the field, but the asphalt keeps the particles from jumping around. Hey, that sounds pretty cool. Yeah, well, it was a real convincer on what vibration can do.
I hope everyone's able to hear that. But really, since this shows it with a bunch of beans that don't have any fractionation to them, but because we have fractionation in the material we're looking at today, the vibration does help it. Looking at that, it does give us a little better advantage of trying to get the initial compaction in the temperature range that we're looking for right away. Just to show here a little bit difference between what oscillation and what vibration is. On the right-hand side, we have a vibratory drum. On the left-hand side, we have an oscillation drum. The vibratory drum has weights that rotate around the center axle and actually lift that drum up off the ground. So 50% of the time, the drum's in the air. The other 50%, it's on the ground. On the left-hand side, on oscillation, the weights are offset from the center axle and kind of give that drum a teeter-totter effect, which we give 100% of the weight of the material, or the weight of the roller is always on the ground, and that drum is moving forward and backwards, kind of giving it that rubber tire kneading effect only with the steel drum. So there is a lot of advantages of where that can be utilized over vibration, and we'll talk a little more about that in maybe the next session. Here's another example of how that looks. Vibration, like I said, 50% of the time in the air, the other 50% on the ground. The oscillation, they call it a transcendental compaction because it's more of an angle forward and backwards. So when we look at vibration, we're looking at basically just a vertical compaction, where oscillation, you have the vertical compaction based on the weight, but you also have the horizontal repositioning of the material as well too because of the action of the oscillation. So now let's talk a little bit about roller trains. Well, a roller train can basically be summarized as a sequence of rollers that are following the paver. And really, the objective is to require that we want to have just enough rollers behind there to require density and provide volume at finish. This is an example of saying we have a range of between 92 and 96% is what we're required to get to a density. We look at 3 rollers here. The problem we see in a lot of locations is everybody tries to achieve all the density with the breakdown roller. If we try to achieve all the density with the breakdown roller, a few things are going to happen. Number one, the other 2 rollers aren't going to do a whole heck of a lot because the temperature has dropped. The first roller is also going to be lagging behind the paver, and everybody's going to be screaming that the roller is not keeping up to the paver. So now we have to speed the roller up. When we speed the roller up, we notice we're not maintaining our density like we did before. Because temperatures have gone down, we're trying to run faster. We're outrunning the roller's capability of getting the initial compactions. So typically behind a screed, we're going to see maybe a max of maybe 80% of a conventional screed. The other thing I highly recommend is making sure that everybody uses the vibrators on the screed to give, because that's free density. That's free compaction. Even if it's 1%, it's 1% less that we have to worry about in the roller train to try to achieve what we're looking for. So we have a 92 minimum that we're looking at. I try to get at least a breakdown roller to achieve 90 to 91% of that. I want to at least maybe get close to the minimum, and so I can keep him in a roller pattern close to that front of the paver. If there's still temperature in there, there's some modifications we can do to the second roller to try to help bring that up even further. The finish roller, we're probably not going to be running it other than in static mode, just to try to take out any other marks or maybe just smooth things off from the back. We also look at the different ranges as far as the passes go. We want to make sure that our roller passes are consistency in the distance that we're running. We don't want to have them short and actual long. If they're too short, we have too many crossover areas. If they're too long, the temperature cools down too much. So we just need to make sure we're consistent. But we do not want to try to achieve all the compaction with the breakdown roller. Now, with that being said, they're also very flexible. Some locations do require the use of a rubber tire roller. So sometimes the secondary roller is a rubber tire roller in the roller train. Same thing applies, and we still don't want to try to achieve everything with the breakdown roller, but we want to make sure that we can get some compaction with the secondary and third roller as well. Now, the other thing about a rubber tire roller, it should never stop. That rubber tire roller should constantly be moving. You're not going to destroy a mix with a rubber tire roller. If it gets into a tender zone, we might need to back off a little bit if it gets too tender, but we definitely are not going to destroy a mix with a rubber tire roller. It should never stop. A lot of people have a tendency to stop on the mat, and they say, well, the tires will stay warm. The problem is if you have the hot spots on the bottom side of the tire, it's the same as sitting off on a cold mat. And instead of having a cold spot, you're going to have a hot spot. So it will change. We just need to make sure that that rubber tire roller maintains some kind of a speed. I don't care if it's just creeping along. It needs to stay moving. And the finished roller can either rerun in static, or we also can use what we call the oscillation on the rear drum to help smooth things out as well, too. So the summary of the roller types. Well, we have the static steel wheel. A lot of people never thought we'd ever get away from that. Couldn't imagine why we'd put vibration on a mix, but because of the mix designs changing and the aggregates that we're utilizing, we needed to have a little bit more effort to get the compaction we're using, especially with the type of loads that we are putting on our roads today. So we're either using it as a finish roller, or we're using it to do some kind of either a pincher joint or something of a real small surface step. Rubber tire rollers, the static weight, the kneading we're also using for proof rolling on some of the base material. It helps seal the matte surface on the asphalt mixes. Very good roller, especially if you have a lot of catch basins, water mains, and manhole covers to try to get compaction around. We also use what we call combo rollers, where these have become more and more popular with a lot of smaller contractors, municipalities, cities. They're also good for very steep grades, so you have the best of both worlds. You have the vibrating drum up front, which helps get the initial compaction, and you have the kneading ability of the rear tires to do that as well. And the other advantage, you can run this forward or reverse depending on how you want to do it. You can finish with this roller too with the rubber tires up front and the steel drum on the back to take out the marks. Very good, versatile machine. Probably the most common that's out there for any roller is the dual vibratory in both front and rear. And we have different versions of this. We also have what we call a high-frequency roller from the standard roller, where we put both front and rear drum into a high-frequency mode, try to get a little more compaction. We can talk about that a little bit more in the next session. Another one is the Aussie roller, where you have the front drum is vibration, the rear drum is oscillation. Kind of a get-out-of-jail-free card, where you can't vibrate, you can always oscillate. If there is temperature left in there, because we are restricted on temperature, on how low we can go to vibrate before we start either damaging the mat or putting some kind of ripples in it. With oscillation, if there's still temperature in there, we can still move that material around to gain a little bit more compaction or density that we need. So in summary, why compaction? We need the ability to support a load. If we can't support a load, we are not going to be able to have that road stay together and have longer lasting roads. What is compaction? It's basically just a manipulation of the materials. On the soil side, when we manipulate them, we need to add proper moisture content. On the asphalt side, the liquid is our lubricant, so we need to make sure we have the proper amount of that as well too. 4 elements to achieve compaction. We have the static, we have the impact, which is more probably on the soil side. We have the dynamic annealing, which is on the asphalt side that we use depending on the type and thickness of the material that we're going to be looking at. Roller trains, really just how many, a lot of times people understand the mixes. They know what kind of rollers they need and how many they need to get the job done. Some locations will specify based on the mix type as well too what we're going to try to use for equipment in our roller train. The roller types, we have the static, the pneumatic, combo rollers, double vibratory, which is the most common, and then also the vibratory with oscillation. So those are the different types of rollers that we are looking at. And with that, again, we look at the second compaction webinar, which is the advanced compaction. Talk a little bit more in depth with the techniques of different things, but definitely a little more in depth as far as the detail of the compaction. And if anybody has any questions, comments, or concerns, or anything else, that's my information. And I think my time is up, and I appreciate the attendance, and look forward to the next one.
Tim, thanks for an excellent presentation this morning. For information purposes, today's webinar is being recorded and can be downloaded on our website by locating the webinar button. And Tim already directed you to our contact page. We welcome your feedback and hope you'll plan on attending our webinar session on May the 7th. And with that, I thank you for your attention this morning. Be safe on the road, be safe on the job, and have a great day.